series of lectures on marine hydrodynamics. In the last class, we have talked about basic equation, basically the Navier-Stokes equation of motion for incompressible and viscous fluid. And then we have talked about what happens when the Reynolds number is very small, and then it leads to a kind of motion which is called creeping flow or Stokes flow or slow motion. As a continuation of that, today we will talk about fluid which are Reynolds number are small, but it is comparatively larger than that of the creeping flow motion. Particularly here we will again concentrate on some of the analytic solution. As I have told in the last class that these analytic solutions plays a crucial or plays a significant role in analyzing generalized flow problems of which are of real physical importance and arises in real world problems. And these problems these simple flow problems gives a benchmarking to benchmark results to when we get approximate solution for generalized flow problems, and also it gives a little bit understanding about the flow characteristics. So, today again as I have told that we will start with some of the basic flow problems and analyze the flows associated with these problems. So, as a simplest one we will think of that I have again talked about one is the one dimensional flow problem, fully developed flow, one dimensional fully developed flow. And what is a fully developed flow? In this case the inertia term is negligible, and one is the inertia term is negligible, and the second thing is that the flow is unidirectional, particularly suppose q bar which has component of. So, here we will only consider as a flow is in the x axis, or it can be considered in one of the axis. So, it is unidirectional, flow exists in one direction and the inertia terms are negligible, and these are called fully developed flows. And there are other flows, some of the cases where we may again look into problems where the inertia terms may be written. So, this comes under this category of flow, and again when we look into this we have two classes of problem, one is steady, one is transient. In case of steady it is a time independent, where in case of transient flow where the time dependent flow with a initial value being prescribed. In the case of steady flow we have no initial data because it is independent of time. So, only the wall boundary condition has to be prescribed. On the other hand, in case of a transient flow we need to prescribe the initial values at time t is equal to 0, what happens to the flow in addition to the wall boundary conditions. So, with this let us look at a flow in case of if I say that I have a fully developed flow, I already have told you that q bar is equal to u I hat, where u is the x component of the velocity, and here if this is then you have the velocity component in the y direction is 0 and in the z direction is 0. If this is the case, then what will happen to for an incompressible fluid, the equation of continuity, it will give us that del u by del x is 0, continuity equation for incompressible fluid. If this becomes del u by del x is 0, and once del u by del x is 0, which is same as telling u is a function of u y z, and if I again say that the flow is two dimensional, flow is 2D, then what will give me that u can be written as a function of u y, because it is independent of z. So, for a two dimensional flow, fully developed flow, we have, if the motion is, we have for an incompressible fluid we have u is equal to u y. Now, what will happen to the equation of motion? If you look at the equation of motion, this gives us two things. Then again, as I say that this will give me inertia terms are negligible, del u by del t, that will give me minus 1 by rho grad p plus nu del square u, and this grad p is nothing but del p by del x, because along the x axis this becomes the equation of motion. And again from y component we have a two dimensional flow, from y component it will give me del p by del y is 0, and once del p by del y is 0, that gives me p is a function of p x only. So here u becomes a function of y and p becomes a function of x only. Then what will happen, and this is the unsteady motion. On the other hand, if the motion becomes steady, this is for unsteady motion. However, if the motion becomes steady, then the equation of motion reduces to this term will be 0, that means del u by del t is 0, and in that case we have del square u is 1 by mu, because it is mu by 1 by mu minus 1 by mu del p by del x. Here we can see that u is a function of, and del square u is what? That will be basically we are looking at the x component of the okay. So, del square u, and here u is a function of y only. If it is a two dimensional, then that will give me del square u by del x square, or del u is a function del square u by del y square. This becomes minus 1 by, sorry, I will come to this later, the next later. So, what it gives, if the flow is a two dimensional, then it gives me del square u by del y square is equal to minus 1 by mu, and dp del p by del x, because p is a function of x, so this becomes dp by dx, and this becomes the flow. Now, this is for the two dimensional flow, and here u is a function of u y and p is a function of p x. Now, if I have to solve this, because this is a function of y and I assume the difference of pressure is known, then I will have del square u by del y square is equal to minus 1 by mu, if this is dp by dx. Since this is a function of x, this is a function of y, I can always integrate it twice to get it minus 1 by mu, that will be 2 mu dp by dx into y square plus a y plus b. So, this is for a steady one dimensional flow, this becomes the general, the flow distribution is u along the x axis becomes of this form, here as a b are unknown constants which are arbitrary and to be determined, they to be determined by using the wall boundary condition. On the other hand, if I say the flow is a two dimensional, three dimensional in nature, just let us see the general form how it looks like, then we will come to specific cases. If the flow is a two dimensional in nature, three dimensional in nature for 3D flows, the flow is 3D, then and it is again fully developed, then I will have u is, we have del u by del x is 0, means because it is a 3D flow, whereas the flow direction and here v is 0, w is 0. So, you have u can be a function of u is a constant and u can be dependent on y and z. This comes from the continuity equation, On the other hand, from the equation of motion, we will have as usual we have v is equal to 0. So, that will give us del p by del z, del p by del y is 0, and again we have w is equal to 0, that gives us del p by del z is 0. In fact, in all these flows I consider either we observe the body boundary condition in the pressure term, or sometimes we neglect that because we are considering flow between. Basically, it is observed in the pressure term. And if this is 0, that if these two things is 0, that means a pressure is independent of y and z, that means p can be written as a function of p x only. And in the process, what will happen to the x component of the equation of motion? This is from the y component of the equation of motion, and this comes from the z component of the equation of motion, and then equation of motion, the x component will give up del u by del t, because inertia terms are negligible. This is equal to minus rho into del u by del t is a del p by del x minus del p by del x. The body force term is also involved with this, plus it will be mu into del square u by del y square plus del square u by del z square, because u is a function of, because nu del square u, that will show u is a function of y z. So, x component does not come into picture, and then when the motion is steady, then this becomes, this term will be 0. So, that will give us del p by del x equal to mu by rho, that will be nu del square u by del y square plus del square u by del z square. So, this becomes for steady case, this becomes the equation of motion, and this is for, whereas here p is a function of x and u is a function of y z in case 3D fully developed flow. So, this is the general form, and here again we need to prescribe the wall boundary condition. To solve this equation, if we are solving this as a steady problem, then only we need the wall boundary condition, and if we want to solve this, we need, apart from the wall boundary condition, one initial condition to take care of the transient part. So, now we will go to simple flow problems one by one. So, the simplest one in this series is the straight parallel flow in a straight channel. Let us consider the flow between two parallel plates. Consider the flow between two parallel plates. So, and this distance between the two plates is I consider this as h. Now, as I have seen, we have seen it becomes a one dimensional flow. I consider it is a two dimensional flow, 2D flow, and just we have seen that for a two dimensional flow, the governing equation we have u is equal to ui, we have u is equal to ui, and p is a function of px only, and then we have seen that the equation of motion that gives rise to u, the flow distribution is u equal to minus 1 by 2 mu dp by dx into y square plus ay plus b. This is the general flow, and here the wall boundary condition, there are two plates, so the side of the channel, and then on this we have to prescribe the boundary condition, which are, once we know A and B, then we can know what exactly the flow distribution. And now the simplest flow of this parallel flow is the Cortex flow, and in case of a Cortex flow, what we do that y is equal to 0, u is equal to 0, y is equal to h, u is equal to u infinity. So, that means one of the plate y is equal to 0, one of the plate, this plate, if it is y is equal to 0 and this is called y is equal to h, this plate is fixed, kept fixed. So, no slip condition will be there, there is no fluid will pass through this. So, horizontal direction the fluid velocity is 0 at y is equal to 0, and then y is equal to h, y is equal to h is along this plate. Look at the plate boundary of this. Then in this plate is, we assume that this plate is moving at a speed u infinity, u is equal to infinity, steady motion, where u infinity is a constant uniform flow. That means this plate is moving at a uniform speed at y is equal to h. And again in this case we assume the pressure is uniform, pressure is uniform. Once pressure is uniform, then which implies dp by dx is 0. So, if I look at this original equation star, that gives me my u is equal to a y plus b, and this u is equal to a y plus b. If I substitute for y is equal to 0, u is equal to 0, that gives me from the equation 1. So, y is equal to 0 at u is equal to 0, which implies b is equal to 0, gives u is 0, y is 0. So, that will give b is equal to 0. Then the other condition, y is equal to h, u is equal to u infinity, because already b is equal to 0, that gives me u infinity is equal to a h, and which implies if I substitute for a is u infinity by h, and thus if I put b is equal to 0, a is u infinity by h, that gives me u by u infinity is equal to y by h. In fact, this is the flow distribution, and this gives the flow profile. Profile of the flow. And if you look at this, how the fluid will be moving, that means u by u infinity y by h, that means if this is the, I consider this as a u by infinity y by h. So, in fact, initially the fluid flow is, there is no fluid is flowing across this, then slowly the speed increases. This is the way fluid will be flowing, and then u becomes u naught, u infinity, here u is equal to. So, the speed goes on increasing from u is equal to 0 to u is equal to infinity, as u by u infinity is y by h, as you go away from the this wall to this wall. So, this side the fluid will not be flowing at all, whereas this side the fluid will be flowing at the same speed, just adjacent to this wall the fluid will be same as the u infinity, and this will be the rate at which the fluid will be flowing. The speed will be this. So, this flow is called a Cortex flow, one of the most simplest flow for the viscous fluid one dimensional flow. Now, I will go to a second example, that is called a plane Poisson flow. Plane Poisson flow. And in case of a plane Poisson flow, what happened? The pressure gradient dp by dx, it is again the flow between two channels, and the pressure gradient in this case the dp by dx, that is this is non-zero, Further, both the walls are fixed, both the walls of this are fixed, that means none of them are moving. Then if you go to the general solution, what we have just derived for a one dimensional, two dimensional flow between two plates, then we have already seen u is equal to 1 by minus 1 by 2 mu dp by dx y square by 2 plus a y plus b. This is our general form of the solution for a two dimensional one dimensional fully developed flow. If this becomes this, then when dp by dx is non-zero, then we have both the walls of the channel are fixed. So, what will happen if I just say that one of the channel is y is equal to minus b and one is at y is equal to b, they are located at a distance 2b. You can always use the same notation, but since there is no harm in always choosing different notation, the distance m, but you can always from 0 to h. Here h is in the previous Cortex flow we have taken this distance as h, here we are taking this as distance as 2b, does not matter. So, u is equal to minus 1 by 2 mu dp by dx y square by 2 plus a y plus b, this becomes the general flow, and in this we have dp by dx is not 0 and we have u is equal to 0 at, because both the walls are fixed. So, u is equal to 0 at y is equal to plus minus b. If u is equal to 0 at y is equal to plus minus b, that gives us, suppose I say u is equal to 0 at y is equal to b, and that gives me u is 0 at y is, that gives me y is equal to b. Y is equal to b means minus 1 by 2 mu dp by dx into b square by 2 plus a b plus b, and this equal to 0, and then u is equal to 0 at y equal to minus b, that gives me minus 1 by 2 mu dp by dx into b square by 2, then minus ab plus b equal to 0. And if you simplify this, then that gives us a as a 0, that gives me, from this we will get a as 0 and b will get minus b square by 2 mu dp by dx. This is obvious because you eliminate the first instant. If you eliminate b, then you get a, because these two terms eliminate b means you just subtract one from the other, and then you will see that this term will get cancelled, this term will get cancelled, because they are of same sign, they are of opposite sign. So, that will give us a is 0, and when you, if you add these two things, then a will be already a is 0. So, you have 2 b is equal to this. So, b is equal to plus b square by mu into, this is what we have got it. Now, here if I substitute for this b, then what will happen to my u? A b u will be minus 1 by 2 mu dp by dx into, this is b square minus 1 by 2 mu b square minus y square, and this is same as, this gives me minus 1 by 2 mu, if I take b square by 2 mu into dp by dx 1 minus y square by b square. This is the general pattern of the distortion of the flow, and here dp by dx is non-zero. So, this is the general pattern, and if I look at the what will happen to du by dy is 0. If du by dy is 0, that means to know where the flow is maximum, it can be easily seen that at y is equal to 0 the flow will be maximum, which implies y is equal to 0. That means, in the channel there is no flow here. So, at this point the flow velocity is maximum, u is equal to v max. So, what will happen to my u max? That happen at y is equal to 0. So, u is equal to u max is minus b square by 2 mu into dp by dx. The question comes, this becomes the maximum. Speed will be maximum, the positive value has to be taken if you are looking at the speed. And then what will happen to u max? In that gives me u by u max if I substitute, because b square by 2 mu if I just take it from the original equation of u, then I will get 1 minus y square by b square, that I get. This is what, and this gives in the velocity distribution for a plane Poisson flow, which is the flow distribution. For a plane Poisson flow. Now, with these two simple problems, very simple problems, now I will go for a generalized plane Cortex flow. If I go to a generalized plane Cortex flow, this is in case of a generalized plane Cortex flow, we have seen that in case of a Cortex flow, plane Cortex flow we have taken, we have the two plates, there are distance h, u is equal to u naught, and that was moving at a uniform speed, this plate was moving at a uniform speed, whereas this plate is kept fixed. U is equal to 0, this is y is equal to 0, this is y is equal to h. And in the plane Cortex flow, so we have seen that we have taken u is equal to 0, y is equal to 0, and u is equal to u naught, y is equal to h. Unlike the case of a plane Cortex flow, in case of a generalized Cortex flow, we take dp by dx as non-zero. If the pressure difference is not equal to 0, then as usual we will have u is equal to 1 by 2 mu dp by dx into y square plus ay plus b. And if this is the general flow, nature of the general flow, then we have again this term will not be 0, but u is equal to 0 at y is equal to h, and then it gives us, if u is equal to 0 at y is equal to 0, that gives us b as 0, u is equal to 0, y is equal to 0, that gives us b is equal to 0, and when then if you substitute that u is equal to u naught at y is equal to h, that gives us a as that will give a as u naught by h minus h by 2 mu into dp by dx. This can be obtained. Just substitute for u is equal to u naught at y is equal to h, and in this equation then you get H this, whereas B is 0 and H this, and in the process you get U is equal to minus H square by 2 mu into dp by dx and minus y by h into y by h into u naught. This will give you. So, so this gives us the general flow, and that is the general expression for u. And if you substitute for this, now if I, in this case if I take a little, define the pressure terms as P is equal to h square by 2 mu u naught into minus dp by dx, then the velocity distortion term gives me in the non-dimensional form, then u by u naught is equal to y by h plus p infinity into 1 minus y by h into y by h. From the previous expression you will get it, because I have taken a negative term there. So, this will give us this. And then once this is the general form, where I have taken in p infinity the negative sign. So, what it says that the velocity distortion depends on the pressure p infinity, and there are 3 cases arise. In case 1, suppose p infinity is greater than 0, p infinity is greater than 0. If p infinity is greater than 0, I have a dp by dx is, so that means this is greater than 0 means dp by dx is less than 0, and once dp by dx is less than 0, that means the pressure is decreasing, in nature. With increase in the flow direction. So, dp by dx is less than 0 gives us pressure is decreasing in nature, and so what happened to the velocity distortion then? And if I just plot it, u by u naught and this is y by h. In fact, you will see, I just take this, then in fact this is p infinity is 0. If p infinity is 0, then u by u naught is, in fact p infinity is 0 means I will call this p infinity is 0, that gives u by u naught is y by h, as we have seen in the previous case. And if it is p infinity is 1, so this is p infinity is 1, p infinity is 2, 3. On the other hand, we have this is p infinity minus 1, this is the case p infinity is minus 2. And here what happened? If p infinity is 0, p infinity is greater than 0, that means the flow is always in the moving in the positive direction over the whole width of the channel. Flow is in the positive direction. On the other hand, when case 2, if p infinity is 0, that means you have the flow speed that means dP by dx is 0, the pressure gradient is 0, and this is similar to the plane Cortex flow, and the flow distribution is, in this case it is linear, and it will go on increasing as we have seen in case of a Cortex flow, plane Cortex flow. And case of case 3, when P infinity is greater than 0 or less than 0, sorry, P infinity is less than 0. P infinity is less than 0 means dP by dx is greater than 0. When the pressure difference is increasing, there is a region on which, particularly in this part, you see that the flow distribution is in the negative direction. That means fluid flow in the opposite direction. There is a chance that flow direction can be negative, The fluid flows in the opposite direction, and what does it means? Because that means the viscosity is drag the motion, and there is a situation which makes the flow to be in the positive direction. It is due to the, basically this is due to the adverse pressure gradient. This is due to adverse pressure gradient which surpasses the dragging action of the faster layer of fluid, which surpasses adverse pressure gradient, which surpasses the dragging action. Of the faster layer of the fluid particle. Fluids. So these are the three cases where in one case, in this case particularly, this is one of the interesting observation that flow can be in the negative direction, and this is only possible when we have this, particularly in the presence of a viscous drag with a difference in pressure. Now, this if I go to what is the, let me calculate what is the volume rate of flow. The volume rate of flow, and this is depend as, if I say Q as the volume of flow per unit width per unit time, I call this volume of flow per unit width per unit time at any normal section. Of a channel. Then this Q is given by is equal to 0 to h, you just integrate it u d by. If you substitute for u the general flow distribution in this expression, that means I know that u by u infinity, u by u naught is equal to y by h plus p infinity into 1 minus y by h into y by h, and if I substitute for this here, then I will get q, you get u naught by h by 2 plus p infinity u h by 6. This becomes the volume rate of flow per unit cross section, and it can be seen that because we have seen that three cases that p can be negative. So, you can easily see that for p infinity is minus 3, if p infinity is minus 3, then this is u naught by h, p infinity is minus 3, this is minus 1 by 2, or this is also u naught h. So, then that will give us q as 0. So, that means when p infinity is minus 3, q becomes 0, volume rate of flow is 0. That means there is no net flow along any section which is perpendicular to the reduction motion when p infinity is minus 3, no net flow occurs. Now, with this I will go for another quantity, that is called the coefficient of skin friction. Coefficient of skin friction, and this is defined as this is the non-dimensional shearing stress in the surface of the body due to the fluid motion is known as the skin friction coefficient. Known as the skin friction coefficient. Is known as the skin friction coefficient and is defined as Cf is equal to tau w by rho u square by 2. And in this case, and tau w is given by, that is a shear stress near a wall, mu du by dy, and this is at y is equal to 0, because one of the wall is at y is equal to 0. And in this case, if we substitute for u in tau w, we will get this will be mu u naught by h, and this is 1 plus p infinity. This becomes tau w, and then in the process my Cf will be, if I substitute for tau w here, then this will be 2 by Re into 1 plus p infinity, whereas my Re is h rho u naught by mu. So, this is kind of a Reynolds number, where h is the typical length parameter, u is the speed, and mu by rho, this is a kind of. So, the skin friction coefficient is becomes this, and it all depends on the Reynolds number of the fluid flow and p infinity the pressure gradient. And again, if you will see that the skin friction coefficient Cf, if p infinity is minus 1, our Cf is equal to 2 by Re 1 plus p infinity, and we can see that p infinity, the Cf, the skin friction coefficient Cf, this is greater than 0 for if p infinity is greater than 0. Obviously, this is greater than 0, and Cf is less than 0 if, that means this quantity is less than if p infinity is less than minus 1, and again Cf equal to 0 if p infinity equal to minus 1. So, we also see that for the plane Cortex flow, for plane Cortex flow, p infinity becomes 0, because dp by dx is 0, and in that case Cf is 2 by Re. So, this is another important observation in this case. Now, with this understanding of we discussed 3 types of flow today. One is the plane Cortex flow, the other is the plane Poisson flow, and the third type of flow I call this is the generalized Cortex. General plane Cortex flow. In all the 3 flow, this is basically we consider the flow between 2 plates, basically in a channel. In one of the case, in the plane Cortex flow, we consider the pressure gradient is 0 and one of the plate is fixed, the other plate is moving the channel, the other plate. That means, here the fluid, and we have seen that the fluid flow increases from 0 to till it reaches the speed, it reaches the highest speed along this other end of the channel where the plate is moving at a speed. On the other hand, when you came to plane Poisson flow, here we assumed as if both the plates are fixed, the channel both the walls are fixed, and whereas dpy the pressure gradient is non-zero, and in such a situation we have seen that the maximum fluid speed occurs at this point. On the other hand, in the case of generalized plane Cortex flow, we have seen there are 3 cases. All this depends on the P infinity, that means the non-dimensional pressure gradient, and also we have seen the volume rate of flow, and volume rate of flow when this P infinity term becomes -3, there is no net flow, which no net flow across the channel under this condition. And the next, with these simple 3 cases, the next problem we will discuss about the flow in tubes of uniform cross section. Flow in tubes of uniform cross section. Again, here when I consider a tube of uniform cross section, of course, I assume here as if the flow is 2 dimensional in nature, 3 dimensional flow. This becomes a 3 dimensional flow. And in case of 3D flow, and again I have the flow is unidirectional. Then when I say flow in tubes, I can have several tubes. I can have a circular tube, I can have a coaxial tube, like suppose I may have a tube, 2 tubes, the inner cylinder is a rigid one and the flow across this and this between the cross section of this. So, the fluid is flowing through this, but there is a closed, this is another cylinder and which may be fixed inside this. There is a flow between 2 coaxial cylinders, and there can be situation I may have a duct, rectangular duct, or I have a square duct. It is a channel whose cross section is rectangular, whose like its front face is square, its front face is a rectangular one, and it is flowing as a large channel. Having the front face is square, here unlike it is a circular one, it is a cylinder. So, the duct is like it is a channel whose front face is square in case of a rectangular duct, in case of a square duct, and in case of a circular duct the front face is rectangular in nature. So, and it can be the fluid can flow in this direction, one directional, let it be in the x direction the fluid flow is there. So, this is all these flow, these are all 2 dimensional 3 dimensional fluid flow, but the fluid is unidirectional, that means again u is equal to q is equal to u I, only in one direction the fluid is flowing. And if I look at the general form of the solution of this problem, again it is also considered under the fully developed flow category, and in this case also, as I say, if I assume that the flow is along the, like I take x and y along the axis along the plane of the cylinder. So, only the, if I think of a cylinder, I consider as if the z axis is along the cylinder, generator of the cylinder. So, if this is the z axis along the generator of the cylinder, and this is x, this is y, then if I do that, then I will consider my u is equal to 0, is v is equal to 0, and I will have only w component, I have only w component, z component, that is w. So, my q bar I can call it a w k hat. I just take this in this case, I can always do any, but for sake of simplicity, if I take the q bar is w k hat, that means u v are 0, and then you will have what will happen, this becomes my equation of motion, becomes equation of continuity, gives me del w by del z is 0, because u is 0, v is 0, and del w by del z is 0 gives me w as a function of w x y. And in a similar way, if I go back to the Navier-Stokes equation of motion, I will have del p by del x is 0, because my u is 0, and del p by del y is 0, because my v is 0, whereas the third component of the velocity gives me del square w by del x square plus del square w by del y square, and that gives me, because this gives me what, p is a function of z only, and then the z component of velocity will give me del square w by del x square plus del square w by del y square, because in z direction there is no flow, and that gives me 1 by mu del p by del z. This will be the, and again p is a, because this itself is giving a p is a function of z, and here we can see that w is a function of x y. So, this part will be a function of x y, this part is a function of z, it cannot be possible. So, this has to be a constant. So, the pressure gradient is constant, del p by del z is a constant ILA, and here w is. So, basically the governing equation will be of this nature, and depending on the flow characteristics, the type of flow in the tube, whether it is a rectangular cross section, whether it is a square duct, square cross section, or whether it is a circular one, will substitute the boundary condition on the wall boundary, and we will analyze this flow in our next class. After this, we will go to some of the transient flow problems. So, let us see in the next class about the flow in the circular, flow in the tubes of various cross section with this fundamental. Basically, we will be concentrating on this equation. With this, I will stop here. Thank you.